So that kind of gives us an idea of how spread out your data is, the difference between the max and the min. So now we know how spread out our data is. Now, ready to start? Superhero day. Superhero. Okay, deviation. This is the crux of your course. Standard deviation. To deviate means to go away from the mean. The deviation that we measure of an entry in a population data set or a sample data set, well, population this one because they use the mu, is the difference between the entry and the mean of the data set. In other words, I have a bunch of data, 10, 20, 30, 40, 50. I take an average. And then I see how far does each one of them go off the average of that data set. That's how far it deviates off the mean. What you guys probably remember last year, when you took Algebra 2, is this graph that we used to do. We used to put the mean right here. Well, we do put the mean right there. Then we measure your standard deviations, and we look for those x values, and we can tell how many standard deviations it was from the mean. A standard deviation is a way for us to measure how far it is from the mean. Anything that deviates is away from the mean. It could be plus, it could be minus. Now, the difference between population and sample is just that with population, we say mu. This is called mu to be the mean. It's just the mean of your population, and when you put it in your calculator, you still have to look at the x bar. It doesn't have a mu. And we're going to do this little special formula today. We're going to do the special formula. The sample standard deviation is the same exact thing, only we use an S for sample standard deviation and sample variance, and a small n, and your x bar is your mean. And this is the only difference you're going to see in the standard deviation. One we divide by how many is in your data, the other one we divide by n minus 1. What this does is, it makes it a little bit tighter on the sample standard deviation, and we're going to see that. We're going to do this ourselves and take a look at your standard deviation. On your student notes that you just picked up, I have this chart. Do I? No? In the back? No. You might want to write these down. This is important that you know these symbols. It will all come from x bar when you put it in your calculator. The difference here will be if it's a sample standard deviation or a population standard deviation. If it's a sample, it has an S for sample. In your calculator, this is your sample standard deviation. In your calculator, this symbol is your population standard deviation. Write this down somewhere because this is really, really important. God bless you. In Algebra 2, we did this as well. We looked at populations versus samples, and you know how to determine a population. Population is all possible things. Sample is just the n whatever that you're using. But in your calculator, S, think of S for sample. This symbol with the little O thing is a sigma. It's the lowercase sigma. Now, the uppercase sigma is this, but this is a lowercase sigma. Always, I probably end up calling it omega, because I always say O for omega, O for population, P-O. It's the little O there. So that is called the little sigma. When you look at this U is called the mu, M-U. They're Greek symbols. And this you're going to do today. We're going to do this on a table. It's not in your calculator, but that's how you find your standard deviation without a calculator. So my goal is to walk through it once without a calculator so that you see where it comes from, because I think that's important. Because if you just put things in your calculator, you have no, feeling on how you got that, what you went through to do, do it, what were the steps. So this way, once you think about how the standard deviations were found, I'm fine with you using the calculator after that. But this is important, and I thought I did put it in your chart. I guess I didn't.
That symbol's on the calculator?
Well, this is the symbols you're going to see in your calculator, just these two. Not this. You're going to see X bar for mean. Your mean always shows up as X bar, whether it's population or sample, because your calculator doesn't know that. But what your calculator does for sample is going to do what we're going to do in that formula, subtract 1 from n. And we're going to work one out all together so that you can see it. Okay, just so that you know what our symbols are when we do this. Okay. So are we ready to do standard deviations to figure it out ourselves? We're going to do the formulas ourselves. So what we're going to do is, we're going to walk through this formula. Population variance. Then we're going to take the square root of it and get the standard deviation. Then we're going to do the same for the sample, which you notice is almost the exact same except for the n-1. So I gave you a chart so that you can put this, hold on, so that you can put this on the chart. Okay. All right, good. Now, we're going to find your standard deviation for your population, and we're going to find your standard deviation for your sample. The long way. The way that I had to do this when I went to school. And then we're going to put it in your calculator and let your calculator show us. But I want you to see where it comes from. You always need to know how to get to something, where it came from, before you can use your calculator. So the first thing we're going to do is find a mean for this. We have 14 scores. How would I find the mean? Add them up, divide by 14. So we add them up, we divide by 14. I'm going to give you this.
Not right here.
Yeah, I know. I've had this problem like all day long with this thing. Okay, let's try this again. I want my pins.
Now go back to Microsoft and it was off.
It was off?
Yeah, turn on slider and back up.
Okay, thank you. But it should be giving me my pens.
You pick black. And you pick
I picked black, but it's not letting me go to my pens.
And
Yeah, but before, oh, there's my color. Okay, there it is. Okay, we're good. So the mean of this whole data set is 76.5. So one mean through the whole data set. We added them up, we divided by 14. Remember, your mean is 1 decimal place more than your data is. So if our data is in whole numbers, our mean is in tenths. Now, our next column says this. This is your x. This is your mean. If this is a population, this is your mean. This is still your x. So whether it says x minus the mean or x minus the sample mean is no difference. I usually use x bar because everybody gets that in your calculator, x bar, and then they say, oh, I can't find the u, so I usually put the x bar. Right now, there's no difference in these two. The same with this. We're going to find these the exact same way all the way down. So we're going to say 81 minus 76.5. And we're going to find these all the way down. We're going to do 67 minus 76.5. You're just taking it in that order. So some will be positive, some will be negative. Okay, I'll give you these numbers. Why don't you find the first two? Why don't you guys find the first two so that I know you're doing it right, and then I'll give you the rest of the numbers. So Julia, what did you get for your first one? Good. So, Mommy, did you do the second one?
Yeah, negative 9.5.
Good. So does everybody see we get a negative when the x is smaller than the mean? Right? Because we're doing x minus the mean. Okay, here's the rest. Ready? 1.5, negative 20.5, 1.5, 21.5, negative 20.5, negative 9.5. So some of these are repeating. 1.5, 12.5, 20.5, negative 0.5, negative 8.5, and 5.5. Okay, so all we found so far was the difference between x and the mean. Whether it's a population mean or a sample mean, we do the same thing. Our next step is to square the differences. Right here, these are the squares. We take the difference that we just found and we square it. So if I square a negative, what does it come out to be? Positive. So all these answers will come out positive. So we put in the calculator 4.5 squared. We get 20.25. We put in the next one, negative 9.5 squared. Bless you. Again, bless you. 90.25. Remember, when you square a negative, you get a positive.
So this answer is always going to be positive?
The answer is always going to be positive. Because when you square it, when you square a negative, you always get a positive, right? Okay. So 1.5 is 2.25. Negative 20.5 is 420.25. And 2.25. I want to see this chart in everybody's notebooks. 462.25. This is the same as the other one, 420.25. 90.25. 2.25. 156.25. 420.25. 0.25. 72.25. 30.25. So these are the difference of your squares. Regardless, again, if it's population or sample. Right now it works the same. Then we come down and we take a total of this column. We take a total of the difference of the squares. So you're going to add all this up, and this totals 2189.5. Fortunately, I can't move my graph because I'll lose it. So I'm going to work up here in this little space. 2189.5. We took the difference of the squares and we summed it. The little e means sigma, sum. We took that whole column and we added it up. Now, 2189.5. Here's your formula for your population variance. We're going to take the sum of the squares, which we just did, divided by how many is in that population. This is your population variance. X minus the u, because we're dealing population. Remember, we said up to this point, Damani, it didn't really matter if we were talking sample or population. The process is exactly the same. So say I say this is your population of 14 test scores. There were no more. It was my whole class, 14. So that's my population. This guy we just found. So we're going to put our 2189.5, and we're going to divide it by 14. Good. Because n represents the number in my population. So we put this in. Actually, take off the square because I'm going right to the, okay. probably should have went to the variance first. Let's not take, I'm sorry, I'm just going to change this up on you a little bit, if it's okay. All you're going to do is erase your square root sign. Don't cross it out. You're just going to erase your square root sign. You're just going to erase your square root sign. This is your variance. So, can someone throw this in their calculator, please? Oh, great, thank you. So, this is your population variance. Okay? This is your population variance. To get your square root, your square root says take the square root of these guys. See it? If you take the square root of your sigma squared, you get sigma. If you take the square root of your 156.39, you get 12.51. This is your population standard deviation. Okay? This is what I had to do every single time. We had calculators for this. You guys are going to do this in a calculator in a little while, but I want you to see where this comes from.
Oh, what did you say? Population?
Population standard deviation. Population variance.
What does it say underneath one?
It says population variance. Population variance. So all we did was take your sum of your squares divided by how many are in your data set. There's your variance. We took the square root of that to get your standard deviation. Most of this course will deal with standard deviations, not variance. Variance is for more like in the manufacturing when they're talking very, very small differences. But most of the time we talk standard deviations. Now, remember when I said up to this point, it didn't matter because the mean and the sample were exactly the same? Okay, so now, we're going to take the sum again. We're going to do it as a sample. And the only difference now, we're going to take the sum of your squares. We're going to take the sum of your squares divided by n minus 1. This is going to give you your sample variance. Do you see what the difference is between the two of them? What's the difference?
The number of the entries minus 1.
N minus 1. Number of your entries minus 1. So we still have your total. We remember that. Sum of your squares divided by 14 minus 1, which is 13. This is going to give you your sample variance. Can anybody just throw that in their calculator for me, please?
168.42.
168.1 to money?
423.
423. Thank you. So we'll make it 0.42. Yeah. See, that's slightly more than what we had before. Slightly bigger. So now, to get your standard deviation for your sample, we're just going to take the square roots of these guys. The rest of the process is the same. This would be only difference. And the square root should give us 12.98. So, our standard deviation, because we subtracted 1 from your n, so we divided by a smaller number, so shouldn't that make that number larger when you divide by a smaller number? It makes your standard deviation slightly bigger for your sample than your population. When we spread it out on the curve, like you did in Algebra 2, it just gives you a little bit more room in between your entries because your standard deviation is slightly larger. So we went through all of this to come out with this. Now, do you have to do this every time? No, you're more fortunate than I was when I was your age. You're going to put this in your calculator. You're going to put this in your L1, and that's all we have. We don't have a frequency. So you're going to put this in your L1, and you're going to do a 1-bear set. you're going to pull up the x mean, you're going to pull up the sx and the omega x. And that's what you're going to get from your chart right now. You cannot get the variance. You can only get the standard deviation. And then I'm going to show you how to get the variance. So, put it in your L1. We're going to square it. I'm going to show you a trick in your calculator. I just want you to go to your L1 and plot all those 14 numbers. Put those 14 numbers in there. Watch how nice this is versus doing this whole table. I'm sorry mine is kind of spread out, but I couldn't scroll down. You get the same exact thing, right? You should. You should get the same thing. So you found 12.98 and you found 12.51. Now I want you to notice you cannot find the variance here. Aaron said the variance is just the square of the standard deviation. Make sense? Because we're stepping backwards. This, we took the square root from your variance to get your standard deviation. To go get your variance, we're going to square it. But I'm going to show you a little trick in your calculator. Hit the words VARS. It's like right next to the clear button. And it says number 5, statistics. So come down to number 3, SX, hit enter, and hit square. Do you get your variance now? You get 1.168.42 when you round it. Okay, do it again. There's statistics. And go to your, you just did your sample? Go to your omega x and hit square. See, what happens is we round it. So if you round and then you square, you don't get back to what you originally had. Agreed? So to get back to what we originally had, we're going to go to VARS, statistics, come down to your sample standard deviation or your population standard deviation, and let the calculator find it for us. Make sense? Yes. So, from here on in, we can use your calculator to find all this nice stuff. We don't have to do the table. But I like you to know where the table comes from for 2 reasons. One, you're taking your sum of your squares, you're taking your difference from your mean. Your difference from the mean is your deviation. It's deviating from the mean. You're also noting the difference between your population and your sample. That's why they're different. Because your sample is just divided by n minus 1. So if you ever wondered why they're different, now you know. So we're doing a deviation from the mean, and we're doing a population versus sample. Your calculator will use x bar for both your population mean and your sample mean. Your calculator doesn't know if you want a population or not, it just has x bar. Good? Questions? Okay. Now, you need to take this off. All right. I put this little information down here. This is important. This is from your calculator, and you might want to say here that this is always your mean, your population or your sample. Okay. And in statistics, we don't get too overly sophisticated, so we say any data entries that lies more than 2 standard deviations away from the mean is considered unusual. And those that are more than 3 standard deviations away are very unusual. Good so far? You guys out? Okay. Alright. Now, interpreting your standard deviations. This is a little hard to see, so if you kind of look at your book, it's page 87. Thank you. Page 87. This is really, really important. Since your standard deviation is a measure of the amount that entry is spreads away from the mean, deviates from the mean, the more your data is spread out, the larger or greater your standard deviation is going to be. The closer together, it's going to have less deviation, isn't it? You have a smaller standard deviation. This is important that you get this. I know this is a difficult one to see, but on this first screen, all your data is one entry. It's at 5, right? Do you see your first one? On page 87, it's the first one. Your mean is at 5. Your standard deviation is at 0. It didn't deviate off the mean at all. It was all the same data entry, wasn't it? So if I have like all these 5s together, I have 8 5s. My mean has to be 5, doesn't it? And there's no deviation off the mean. This next one is kind of like your bell curve. This is more your normal curve. Your mean is 5, and your standard deviation, you would have to calculate this way, is about 1.2 they calculated that, and we'll get a little better at figuring that out. This one here, notice, the mean is 5 again. And look how far apart your data is. Your data is really far apart, isn't it? It's really deviating off the mean. So that one should have the largest standard deviation. That's the point they're getting at. Less deviation, no deviation at all, 0. A normal deviation, a little bit more. And a large deviation should have the largest standard deviation. So do you see it? Okay. So take a look at the one underneath. Example 5. That's this one. Tell me which one has the largest standard deviation. Aaron. The last one, the one on the right, because they all got the same information. So you say that one has the largest standard deviation, right? They just gave you the n in this case. The n and the mean. They all have the same mean. This one, again, what would the standard deviation for the first one be? 0. It doesn't deviate off the mean at all. This one here, what would you say that standard deviation is? 1 on either side. Remember, the mean sits in the middle. You go +1, you go -1. So there's only one difference from here to here. So that standard deviation is 1. And the last data set is the most spread out. So that makes sense. Well, yeah, we'll probably have to take a little bit of an average here and figure out that data set. But more so that you kind of get the hang of how spread out this data is. How'd that look for standard deviations? Okay, I'm going to have you try some. And let's give you these to do. You can use your calculator for these. Well, then you come to the wall and you get one. Then you should have rented one. I gave you the opportunity, right? I gave you the sheets if you need to rent one. Calculators. We said the first one, since most of you don't have calculators, let's do like 5 minutes now, well, 3 minutes now. Sure. And maybe like the first 10 minutes of tomorrow. Who needs to rent a calculator? Yes. I